Right, so what I'm going to do is take off from where Rafael left yesterday. It's a very hard job to do because this is a complex field and it's hard to sort of summarize it in a couple of lectures. But what I thought I should do, because there were some questions that were asked about what is a general framework, what is a co-event, things like this. So I'll try to be a little bit more formal today, just giving you definitions. But then do remember the examples that Rafael gave to give you an idea of what exactly I was talking about. I will also give a few examples. The point of giving these examples is only that they illustrate in a concrete way, not to say that that sort of represents entirely or it's just one particular example and has nothing universal about it. One is trying to use it as an example and get universal concepts out of it. So even the experiment that Rafael showed yesterday is supposed to illustrate the idea of preclusion, the idea of what one means by a reality, and that general notion of preclusion will extend to all systems, and that's sort of what this whole approach is about. So there are two words that we have used. One is quantum measure, and the other is a co-event. Importantly, this whole approach, in the way I like to see it, and I think this is how Rafael envisioned this approach, is to think of quantum mechanics. He talked about it a little bit yesterday, but is to think of quantum mechanics not as a generalization of classical deterministic system set in phase space with Poisson bracket algebra and so on, but rather by looking at the mathematical structure of a stochastic theory, a classical stochastic theory, and generalizing that in a very precise way to quantum theory, to get quantum theory. That generalization is what these two words, expressions are supposed to represent. Quantum measure is a generalization of probability measure, and a co-event is something that is there in classical stochastic theories, but we don't think of classical probabilistic systems in quite this way. And that also gives you, so this approach also gives you a new insight into thinking about just classical stochastic theories. So I'm just going to say some words right now, and then I will define things more precisely eventually. So in other words, we have a measure, and the idea is you take a probability measure and extend it to quantum measure, and we will define precisely what we mean by this object here. But that isn't enough, because we also need to interpret what the structure is. And this interpretation or logic is what the co-event is related, the idea of the co-event is related to. And in the case of probability measure, so in the classical situation for probabilities, you'd imagine, well, what is the issue of interpretation? And in fact, there's a history of probabilists worrying about what does it mean to say something happens. Think of a singular event. Take the event that is going to snow in Bangalore today. Okay? Set of measure 0 will not happen. So singular events and how they're interpreted is something that probabilists worried about a lot. And so there are two ways of thinking about even classical probabilities. One is what Rafael already talked about, the idea of preclusion, which I just said. It will not rain today, that event is precluded. I mean, it will not snow today, sorry, in Bangalore. And interestingly enough, something that was the way people thought about probabilities for a very long time, until the 60s, apparently. People like Kolmogorov, Borel, Levy, then a host of others, Hadamard, Bernoulli, and others. But then there's a frequentist interpretation. Sorry?
Bernoulli should come long before.
Yeah. But Bernoulli was before, yeah. So I'm saying that tradition continued until apparently continued. I mean, if one is to believe the particular history of this that I've read, but then there is also in Kolmogorov's writing and so on an indication of this.
Oh, yeah, it's not explicitly in Kolmogorov.
Yes.
Supposedly in Borel's, although
Yes, Borel has a very nice. So Borel has a quote which I shall read to you just now, which is that the principle that an event with very small probability will not happen is the only law of chance. To think of everything about probability only in terms of events with very small probability not happening. Okay, so this is a notion of preclusion. But then we have the frequentist notion, which is something that physicists have become completely used to. So we don't think about probabilities because we only want to think in terms of ensembles. Okay? But this way of thinking about probability allows you to talk about a single system and still assign probabilities in a meaningful way. And what is, to me, very beautiful about this generalization of thinking about quantum theory as a generalization of classical stochastic theory is not only is there a generalization of this measure, but one also wants to then generalize this, use a particular interpretation and use it to generalize the logic of classical probability theory. So what we want to do with a quantum measure is to use preclusion, so not the frequentist interpretation of probability, but use preclusion, and so can people read it or?
No,
okay.
the plus is the
Okay.
you
So I
can't
just,
read below
okay.
the
Preclusion plus this notion of primitivity, which all of this hopefully I will try to define by the end of this, which gives rise to the notion of a coevent. Okay, so I just want to lay out the structure and then we'll fill in the details of what's to come.
What was that quote by Borel? Is it? Maybe you can tell me later if it is not so
No,
important.
I'll just say it again. But it says that the principle that an event with very small probability will not happen is the only law of chance. So the idea that all probabilities, every interpretation of probability arises out of sets, or out of things that will not, almost surely will not happen. Just so from zero measure sets, if you like, or almost zero measure sets. That entire probability, anything that you give meaning to, will only arise in that way. So this is a very, it's not a trivial statement at all, and I think it's a very hard one to
Very
kind
hard
of,
to try to understand.
yes,
Events which have about 50% chance of happening. Those are the
I
hardest.
suppose
From this
so,
point of view, those are the hardest to understand.
right,
From this point of view, it's a meaningless statement in itself.
yes.
Yeah.
So I mean, if it's 50% chance that it's going to be, I don't know, it's
I
going
think
to
what
reach
it says
30.
what it says is that if it is 5% chance of something, and you have only one observation like universe, only
Then
one
it's not likely to happen.
then it will not happen.
Yes.
Only the 90% things will happen.
Yes, I mean, in fact, you're talking about really vanishingly small probabilities. So, where you make the cut, I mean, so there's a lot of issue of where you make the cutoff, and these are subtleties. But the idea of preclusion, I mean, we will use it in a very much more straightforward way. Actually, sets of measure zero will
So,
not
as
happen.
I understand, the basic motivation was to use the notion of probability for individual systems rather than in some.
That's right. So that is
now
what.
if that is the motivation, then this sort of statements, so when you make so vanishingly small probability, then only you can make a meaningful
Yes.
statement about probability for an individual system.
Right.
But what you mean by vanishingly small will depend on the
Right.
context.
So in the particular cases that we would look at, and this is an issue, and this is an open question: how do we define? How do we do it for things that are quote-unquote approximately precluded. How do we define things for approximately precluded situations is much more complicated, but in the simple systems that we encounter, absolute preclusion is enough.
Yeah.
Set of measures 0 will not happen. And that's enough to carry over. That's simply the lesson to carry over in the quantum context, where even that statement is not an obvious statement. Okay? So, yeah.
This particular example, this snow in Bangalore, for instance. So here, some kind of Bayesian notion is being used, like a notion of a prior, that from an integrated experience, we know that it's very unlikely that we will.
But I could have just had, I mean, it's true that if I had to infer what the probabilities for these various things are, I would need to have checked over the last 200 years record of the weather patterns and then decide that this is a small problem. But then if you just think of it as a probability measure in the space, all one is saying is that that event occurs with very small probability, and therefore, so it's just that if you can construct a probability measure out of older records, then you can make this statement. That's my understanding.
But you could also have a theory that gives you the probability. People do now.
Yeah.
They simulate the weather, and
So that is how the
they
weather report tells you 30% chance of rain.
yeah, you no longer have to just look at the historical record and see how many.
If you look
Days
at the
it
record, you are
rains.
just seeing the ensemble
It
of the
is-
system.
What?
If you look at the records, you are just studying the ensemble of the system and trying to have the statistical output of that. But if you have a theory and if you have only one observation, then you can do that kind of model.
If you have a
Yeah.
theory
That's
that
what
you
they do
trust-
nowadays, I
we
think,
do
for
that.
Yeah,
weather
I don't know
prediction.
about weather theories.
They have some reduced model of, I don't know, if you have a big computer, maybe 10 variables, but if for a poor country, then maybe 2 variables. And then you just put a probability measure on that space. And that is why you can get numbers like 38% chance of rain. What does 38% mean? But you see numbers like this in the newspaper all the time.
The other thing that might not be clear to everyone is how the frequentist way of thinking is in some sense a special case of the preclusion principle.
Right. So in fact, Kolmogorov himself sort of has these two statements. One is the frequentist one, and one is the preclusion one. And the claim is then that preclusion implies the frequentist model.
Yeah, the point is you can always think of the ensemble as a single system, and then it's an application of probability once. But you look at events that in the ensemble are extremely unlikely. So
Right.
like
So you
in
look-
flipping a coin a million times, you could look at the frequency and say you'll get about 500,000 heads, but you could also say what's the probability for that whole ensemble that I'll get 10 sigma away from 500,000 heads. And you compute that and it's 10 to the minus 50 or whatever it is. And so you say, so that's one, yeah,
It's a
the whole
single
ensemble is
system.
one, that's one event that that's precluded, approximately precluded, and so you're willing to say it won't happen. And you're willing, and then if you did get 10 sigma away, you have to be willing to say, well, I reject, my theory was wrong. This was probably a weighted coin.
So in this sense, both are related, the preclusion.
In this sense, the one incorporates the other, yeah, the one is a special case of the other. That's why people like Morel, I guess, were saying that the only real law,
Only real law is this. and we
because
don't-
all the others
Yeah. So
follow.
maybe I should write that
Okay.
in a
So the frequentist thing follows from the
follows. It's a very useful thing to do if you can prepare ensembles and so on, but as a fundamental way of, it's a fundamental way of thinking about probability. Preclusion seems to be more fundamental.
I mean, this comes up, cosmologists, struggle with this all the time. They invent very strange terms that don't seem to have any real meaning, like cosmic variance, to express the point that we have only one sample of the cosmos.
maybe one realization.
Yeah, only one.
Yes. So, therefore, the thing that I want to emphasize here is that essentially this generalization is not only at the level of the measure, it's also at the level of the interpretation and logic, and in a very specific and precise way. This generalization is done in a very specific way. Yesterday, Rafael introduced various structures. One was the history space or the sample space. A more familiar notion would be that of the sample space, which is omega. I'm just repeating some of these things just to, just to sort of, because I think they're not always very familiar with people. So this sample space, you can, if you like, if it's easier for you to think of it like it, just think not in terms of history space, but just as a standard measure space. And what one is trying to do is generalize that measure space in a very specific way. So this is event algebra for the set of questions, and mu is your measure. And at this level, just for the structure of the theory, without its interpretation, what you're doing is you're taking the classical measure and you're replacing it with a quantum measure, and I will explain it, what I mean by this, without changing anything else. So you're not changing the set of questions. You're not saying this is not a question you can ask. To me, that's a very, it sounds ridiculous, but if you think about how quantum mechanics is taught to you, this is one of the things that you have to struggle, I had to struggle with the most, that you're not allowed to ask certain questions. Here you can ask those questions, the same questions that you wanted to ask in classical theory. But of course, what answers you get and how you interpret those answers will be very different. So this is one of the nicest things about this, because you generalize it in this very specific way. Okay, so this event algebra has a certain structure, and I will come to that in a bit. And the best way to do that is actually to go over the classical stochastic thing, a very quick walk of the random walk. And I'll concentrate on just a very small part of the random walk. So again, this is an example which is useful to keep in mind because it teaches tells us something universal about the structure of the theory, not because one is trying to, it's not particular to this example, but it's supposed to be something that gives you some universal understanding. So let's just look at just 2 time steps. And we have it on the lattice. And I'm just going to partition it because and I don't allow it to stay. So it has to either go to the left or the right. And I have these 4 paths that are possible. Okay? So these 4 histories are possible. Right? These 4 paths are possible. I should keep my glasses to read. I'm going to call this gamma 1, gamma 2, gamma 3, and gamma 4. These are the fine-grained histories. And so omega is, let me just call it, just has 4 parts in it. So this sample space has just got gamma 1, gamma 2, gamma 3, gamma 4. And now the questions that I'm going to ask of this will depend on how I wish to partition it. I could ask, well, does this particular path happen? That's an event. But I could also ask, this gamma 1 and gamma 2 and gamma 3, if I just partition it in this way, then this is return to origin, yes? These 2 return to the origin, these are 2 parts, so I can ask, does this return to the origin? That's the event. Okay? Event is returns to the origin. So I don't want to put the question there, but that's the event. And the event does not return to the origin is here. No return. Or I could say only stays to the right, which is this, right? only keep to the right, and this only keeps to the left. So I can partition my omega into the, basically what I'm doing is I'm getting the power set. Okay, I have 4, so omega is the number of elements in omega is 4, and the number of possible questions I can ask, because it's a finite set, is 2 to the omega, which is 2 to the 4. So I have exactly 16 questions I can ask. And what is it that I require of this algebra, this event algebra? In this finite case, all I require is the following. The reason I'm saying it's 16 is I've just constructed the power set. Is because I require that for an algebra, for an event algebra,
diagram is a bit confusing. Sorry. So you start from the origin, and there are 2 possibilities.
No, at the first step there's 2 possibilities,
Yeah.
and then at the next step we have 2 more possibilities.
Yeah, but you haven't labeled the other ones.
I'm just calling the entire path gamma 1. So this is a fine grain,
All the way
the most detailed path that you have, information. So, okay. So what I want for this to satisfy is that if, so I mean, of course this is a power set, and I could decide that these are not the questions I want to ask, but I want some other event algebra. What I need it to satisfy, if it is an event algebra in the mathematical sense, is that it has to satisfy the condition that if A, then A complement also belongs to A. Okay, so for any subset, I also need that it's, because this is all finite objects that, yeah, this also means that intersections belong to the algebra. Okay, so I could do a more coarse-grained version. I've given you this finest-grained one. This is the finest-grained algebra that I can have, but I could construct sub-algebras from this, sub-event algebras, which were more coarse-grained. And this kind of concept becomes very important when you're trying to think of how to get coarse-grained observables in a system. But for now, let me leave it at that. So what is the structure here? I'm going to drop a figure here, which I think will be useful. Yeah.
The algebraic structure is just what Rafael said yesterday.
Yes. So
multiplication and
it's this.
addition.
Well, so the algebra is, at some level, this is just a field over a set. Okay, this is all that is required in the sense of measure theory. This sigma algebra and so on. You can put an additional structure in it, and that's what he talked about. And that additional structure we don't need at the moment. Okay, sorry.
You need to know how to multiply elements and add them.
Not right now. I mean, at this level, no. Only when I put a measure. So when I start to...
I thought algebra is something you could... So you're saying
No,
it's
so
not-
this, we've got different definitions of it. So this is sigma algebras are also called sigma fields, and they're not related to algebras. So Rafael is a better person to answer that question, but basically they're 2 different... I mean, it's a very confusing terminology in measure theory, which they use the same word algebra that you use in linear, in algebra, right? I mean, but it's not quite an algebra in the same sense.
Well, I
So
think-
Rafael may illuminate us.
Yeah, I think it's just a question of terminology. So if it's a collection of sets which is closed, like you said, which is closed under complementation and union, and as you said, it's also closed under intersection. And as you said, people call that an algebra or set algebra. And if it's closed under countable union, they call it a sigma algebra.
Mhm.
And or sometimes they say sigma field, I think. I can't even remember. There's also they say sigma ring and so on. but so there's different
Yes, so
terminology.
ring is used often.
Ring is sometimes if it's not, if you don't demand it to be closed under complementation, but you demand it to be closed under intersection and union. But now infinite countable intersection and countable union, then it's a sigma ring and so on. But it is true that if once it is an algebra in that sense that they use in measure theory, it's also an algebra in the other sense.
You can, yeah.
By redefining the instead of taking the basic operations to be union, intersection, and complementation,
Yes, you take it
if
to
you
be.
take them to be intersections still, but this symmetric difference, as it's called.
So this is a symmetric difference. So this structure,
Then
I
it's
will not,
still-
yeah,
yeah,
then
then
it's
it's
still
an
an
algebra
algebra, and
in-
that's what you can use.
It's a
with-
sense of that's used in when people talk about vector spaces and algebras. So something that's a vector space over a field and it has an addition law and a multiplication law, which is distributive over the addition and all the usual. So in the study of abstract algebras, people, it is an algebra in that sense too.
So the reason I just asked was just to, in that sense, can one think of these fine-grained histories as just generators of that algebra? Because I have these fine-grained histories and if you do
Yes.
that operation, then they generate the algebra. Just to check.
In the complex case, in the finite case, yeah.
In the finite
In
case,
the-
you
Not,
will.
not in the.
Not in the
In
infinite case, it's more.
I see.
Yeah, because the fine-grained histories will not, in fact, belong to the event algebra.
Sometimes they
They're
won't,
only
sometimes
limited.
they won't.
They will, yeah, sometimes they do, sometimes
will.
they won't,
Depending
but
on
they
what
don't
you touch.
have to.
But in any
So-
case, if you think of,
Yeah, so you can generate it through other things. In fact, you could generate that algebra through. So I'll try to say a few words about it. But basically, you would generate it through. In the case of the random walk, you generate it through finite time paths. You could generate the entire algebra of the infinite time case through finite time paths. Through something called cylinder sets, but let me just. So you can. So let me just finish. I'll just finish this, and then I just want to make a bit of a. Otherwise, I'll just get. So importantly, this means that omega is an element of A, and so is the empty set an element of A. And in the infinite case, so the case that we're talking about, you have. So when the event algebra when omega has an infinite number of elements in it, then you would basically require that the event algebra is closed under countable unions. Okay, so and this is also true. So B prime would be what you'd replace it with. Okay, so it's closed under countable unions. But now the thing that you have to do is, so these are what are called the measurable sets. In measure theory, this is what you call measurable sets. I thought I'd finish very quickly, but I don't think it's really possible. And so these are the measurable sets. And the question, like you said, so how does this algebra generated? Or you can even say, how are these sets? Is there a basis for this? So just from a set theoretic point of view, is there a basis that will generate all sets? So in this case, even if from the Boolean lattice point of view, which I'll just draw this Boolean lattice, because it's a useful thing to keep in mind, I find it useful. You have the empty set at the bottom, you've got 4, so I'm going to call them 1, 2, 3, 4. Then you have
that's your gamma 1, gamma 2.
yeah, gamma 1, gamma 2, gamma 3, gamma 4. And this is basically this lattice, when you go up, it means set inclusion. So 1 includes the empty set, gamma 1 includes the empty set. And then you have the intersection 1, 2. So this is, 3, 1, 4. So you've got 6 of these, of course. 2, 3, 3, 4, and 3, 4. And then you combine them into suppose there's more than two of these because you have, right? So do you get? Is this clear what I'm doing?
No,
We're
it's
just
not
basically
clear.
doing setting.
It's